idea of the binomial distribution. The binomial distribution is where we talk about a certain type of situation with an n, a p, and x. N is saying that we have a specific number of observations. We're like talking to a specific number of people. Let's say n was equal to 20. And then we have this letter p, which stands for the general probability. It's very important to understand that general probability is not something that we actually observe. The general probability is something that has to be given to us outside of the problem. So, for example, if we're talking about how many people own a snowblower? Snowblowers are handy to have, but not everybody's got one. I don't have one. I had to have somebody from across the street come over and snow blow me out because I had 3 feet of snow all around my car. It was going to take me a long time, but they just came over and made it happen, which is nice. So let's just say that that's 0.10, 10% of people own a snowblower. So then x is out of n. X would be the thing that we observe. X is the number of people who would say, yes, I have a snowblower. And so that is our data thing. That's the thing we're observing, is how many people say that. And what we want to be able to do is to kind of know what to expect in that situation. And so then if we do that, and we talked about this a little bit before, that there's some software out there that we can use that will just tell us what those probabilities are. But there's a formula. We talked about the formula as well. But if I'm going with binomial distribution, and I have n is equal to 20, p is equal to 0.1, then I get something to happen here. And I can put this down a little bit. Scrunch this down a little bit. And, well, I'll just pull the screen. That's fine. So in this situation, I'm talking about what to expect. N is equal to 20, p is 0.1, and for various x values, I'm using the idea of the tree diagram to figure out what are the things that can happen. It could be that nobody has a snowblower. That would be 0.9 to the 20th power. That would be everybody says no. So I multiply those probabilities, I get this. But then I have other things that could happen and various things that are more likely to happen, right? This is a bit above 10%. These over here, some of them are down below 5%. So we would say that would be unusual. If only 10% of people own a snowblower and I asked 20 people, I would be surprised to have 5 or more people say yes. So then if that's my surprise, then I would expect anything between 0 and 4. So it's like, all right, there's 20 people in class. I need a snowblower. I'm going to ask. And then I'm going to kind of expect that, yeah, somebody's probably got one. It could be that nobody does, but chances are there is somebody who does have one. But if there, if I ask and there are 8 people out of the 20 that have snowblowers, I'd be like, wow, you guys are snowblower addicts. You must love those things. Everybody here loves them, or whatever. So then I'm figuring out what to expect. However, there's something mathematical that happens here when we have large values of n. So let's make this, instead of 20, let's make it 200. When I have it become 200, then I get this thing, and it no longer looks like a collection of rectangles. It looks like a mathematical thing. It looks like a curve. And if I make this 400, it's still that same curved shape. So that when I get to large values of n, and you know, I could change my probability even. I could make this a 0.3. Well, maybe not 0.35. Nope, doesn't like it. Let's go 0.7. Okay. I'm changing my values of n, and I'm changing my probability numbers, but the curve looks the same. It's doing something mathematically the same every time. And so then the question comes out, well, what is this thing? What is happening when I do the binomial distribution and I have large values of n, and it seems to be giving me the same mathematical shape? Well, we need to understand how that works. And so we need to know about Plinko. I think this is mic drop, right? Plinko. What is Plinko? Anybody tell me? It's a game on The Price is Right. Yes, it is. Scott, you know of this game?
Yeah, it's a bunch of metal rods sticking out and then a piece of glass, and you drop the coin and it goes all over. It's pretty accurate.
All right, so we've got a bunch of things that are here, and then you drop a disc up here. It bounces in among these things, and it ends up in categories here. You win money depending on where you go, right? This is like the binomial distribution, because you have a probability of either going to the left or the right, but it's pretty random. And then this is like a tree diagram. Every one of these is a choice. And then those choices can either move the thing to the left or move it to the right. Now, question would be, if I did this 1,000 times, where would I expect this to end up? To the far left, to the far right, or in the middle more of the time? In the middle. The common understanding here is if I have things which randomly can move it either one way or the other, then many times they'll just cancel each other out, and I'll end up somewhere in the middle. But it won't be exactly that. And it's certainly possible that I would have some times when it would go all the way to the left or all the way to the right, but I would not expect that to happen very often. In a similar way, if we have a binomial distribution, even if our probabilities are not 0.5, once again, the same thing would be true. If we have things that might go to the left or might go to the right, they would, at some point, they would cancel each other out somehow. And then the same thing is true about various measurements that we would make. Say, for example, the height of a person. You are not as exactly tall as your parents. Your parents are not as exactly as tall as each other. Because if we go to 6 decimal places, it wouldn't work, right? So there's not an exact relationship where we know exactly that you are as tall as your parents. And there's quite a bit of variation between maybe your own brothers and sisters, right? So not everybody is as tall as their genetic relatives. There's a lot of genetic variation that would cause some people to be taller or shorter than others. But then there's a bunch of other stuff too. I don't know what those things are. I'm not a genetic person of growth hormone whatevers. But the fact of the matter is some of those things might make people taller and some would make them shorter. And so then most people, as it turns out, come out to be relatively average in terms of their height. Is it possible that all the factors would line up for someone to be taller than everyone else? Yes, but that's not the normal thing. What normally happens is that some of those things cancel out and most people are in the middle. Well, I want to make sure that my video is working here. So, what I have here, this is like a Plinko board. You see the metal rods right here, you see the things right here, and I'm going to tilt this so all of these little grains of sand or whatever they are going to be in here, and then I'm going to tilt it so that they all go through like that. So this is like doing Plinko 1,000 times or whatever. So I want to make it so that you can see this on the video. And there we are. And it's bell-shaped. Okay? So a lot of them ended up in the middle. Now, Jeff, can you look here? You have some that are all the way out on here. Some, yes. Yes. So even in this situation, when we have hundreds of these things, there are some of them that end up all the way over here and some that end up all the way over there. They had to have bounced in such a way that they would go all the way over there based on bouncing here whatever number of times. But most of them are not on the fringes. Most of them are in the middle. This is common, and in fact, we might say it's normal. And so we call it the normal distribution. Okay? This is the normal distribution. Now, there might be other reasons why people call it normal, but I don't care. That's the name. It's the normal distribution. It's the definition of bell-shaped. How do we know what bell-shaped is? It's this right here. So then when we ask the question, what do we mean by that really? Okay. I want you to take a look in your textbook, if you can, on page 359 to 361. That's where we want to go. Which means I have to get there too. So we are looking at the mathematical properties of this thing called the normal distribution. And what's going to happen is that much of the mathematics of statistics depends on this particular thing. It has special properties that other kinds of mathematics don't have. And so then it's what we use. So if you look at some of these graphs as you see them, you'll notice that it is symmetric. And certainly we can see that from what we had up here with the, if we had the binomial distribution with large values of n, it's symmetric. It's the same on both sides. It has the highest point in the middle, and that's also the mean or the average. And it's also the median, and it's also the mode. It's in the middle, and it's the highest thing, and there's 50% on one side, 50% on the other side. Now, if you've taken some calculus, it's interesting that it has points of inflection. Does anybody know what a point of inflection is? You might have studied it at some point of calculus, but it's a point where your slope is going to change from negative to positive or vice versa. And so you have this thing it's going down, and then it's actually the curvature changes. So it's curved, it's like this. I shouldn't say the slope, the curvature. The curvature changes. It's like this here, but then when it goes out towards either side, then it's curved so that it no longer goes directly down, but it's actually curved in an upward sense so that it goes down slowly. There we go. So then what we say is that the normal distribution has tails, and that's very important to us. When we have the normal distribution, put that graph up here so we can see it again. So what we're saying for this thing then is that a lot of it is in the middle, but as it goes down, it decreases slowly on the left and on the right. And these things, of course, as we mentioned earlier, this is where the unusual values happen. So this is where our attention is going to be, on the tails, because the tails indicate us what is the unusual thing. And so we're going to use this normal distribution in order to figure that out. So you need to become kind of familiar with those properties, what it looks like. And if you go to page 361, you see the actual formula for this. The formula for the normal distribution. And what you will see is that the formula has an exponential in it, has pi in it. So this right here, this is the formula for the normal distribution. We are not going to use this formula because we don't really care where the value of the curve is located. What we're interested is in the area of the curve, which would be the probabilities on the left or the right. And so when we're looking at this, we would have to integrate this if we were using calculus, but we're not, because we're just going to find out from the computer what these numbers are. And we're also going to use a chart on the textbook. If you want to, you can use a chart. I recommend that you figure out using technology how to figure stuff out because it's more exact and faster. And we'll talk about that in just a minute. All right, so we're not going to use this formula. We're going to either just use calculator or computer to figure out the things that we need. But what we have then here, though, to start with, we're not going to use that entire formula as it stood right there. We're going to talk about something called the standard normal distribution. The standard normal distribution is an artificial data set. It has a mean equal to 0 and a standard deviation equal to 1. This artificial data set will be useful to us because we'll be able to use it to understand how this thing works, and then we'll go to the regular normal distribution. But if we say that something has a mean of 0 and a standard deviation of 1, then hopefully it's easy to understand. It has to have positive values and negative values. So that's kind of what it looks like there. And the variable that we're using here is the letter Z. Z is the value of these numbers on the horizontal axis. Now, if you want to look at the table in the textbook and see how that works, then that's okay. But it's, again, also helpful to understand the technology and how that happens. But the basic concept that we're going to use here is that I want to have some kind of an interval. Let's just say Z is less than -2. And I'm going to look at that interval, and I'm going to find out these three things. The area, which is the same thing as the percent or the proportion, which is the same thing as the probability. The basic question that I'm going to ask here is, how much of the data is in that section of the graph? This is like a histogram, okay? This thing here is like a bunch of rectangles of histogram telling me a bunch of different probabilities or percentages or whatever. But when I put them together, then I'm getting an area. If you do stuff in calculus, you're integrating. But it's also the idea of what percent or what proportion of the data is out here. And if I say that there's a certain percent that's out there, then that would also tell me what are the chances of being out there. So I'm predicting, based on this, how likely is it that I would get a data value less than -2. So then I have to figure out how to find that. Well, if we use the textbook, then there's various ways we can make that happen. If we use our little applet situation here, stat calculator, normal distribution. Okay, so I now have a nicer diagram because it's computer generated. So here I have a mean of 0, standard deviation of 1, and it should say Z instead of X. And less than. Okay. This particular website uses X, but just about everybody else says Z. So what I have here then, what I have here then is when I'm dealing with how likely is it that something would be out there? Not very likely. The probability or the area out there to the left is 0.02275 or about 2%. So it's not very likely to happen. And I could put any other kind of number in here. I could put in 1.4 or 1.47. Okay. So that would be, what is the area from 1.47 to the left? And that would be about 93%. So that's a lot of the data from here down to there. So what's going to happen in your homework is that you're going to have a lot of questions that are going to say, find the area for Z less than a certain amount or greater than a certain amount. And you can use anything, StatCrunch has it, There are some tables in the textbook that you can use, which will go through and you can look up the numbers on the table if you want to. But all the technology is out there for you to use, so I expect you to use it. Microsoft Excel also has a command to find this, and the instructions for that are in the textbook. So you can look up any of these area numbers. Now, there is one situation that comes up relatively frequently, and that is to find the area between two values. So let's say I want to find the area between z equals 1.47 and z is equal to 0.6. So then what would that actually look like in symbols? It looks like this. This would be the probability that z is between these two numbers. That's how we write it. The smaller number to the left, the larger number to the right, and then with the inequality symbols like this. So I want the probability, which is the same as the area, or the percent, how much of the data is in between these two numbers. Now, this particular software might not tell me that, okay? But if I look at this picture, here's 0, here's 0.6, here's 1.47. I know that all of this area over here to the left is 0.92922. And then if I looked up that area for 0.06, or 0.6, that's 72575. So this part here, 72575. So then I say, how much area is in between them? Well, I just subtract the two numbers. So that'd be 92922 minus 72575. Which might be that. I think that's right. So then this would tell me about 20% of my data is in this section. And again, this is all based on a pretty complicated mathematical formula that we're not using, so that we can just either look these numbers up or use technology to find them. But this situation where it's between two numbers, the software might not have that. So then you can just use looking up each one separately and then subtract the two to find what's in between. All right, does anybody have any question about anything so far with these things? Okay, so then when we're working with this, there is a special notation that we have, which is z sub alpha. And this alpha, we're going to change its meaning later on. I'm sorry, this happens a lot. But alpha is here, the area to the right. So then if we say, all right, how am I going to find this? If I know the area, I need to figure out what that z-score is. So for example, if I want z of 0.01, that means I want to know what is the z-score that has 1% as a tail on the right. Well, software can do that, okay? if I want the probability that it's to the right, that would be greater than, and I want that to be 0.01, I just put it in and it tells me. And again, you can use Excel, you can use StatCrunch, whatever you want to use. Again, there are tables in the book that show you this information as well. But if we do this, then we find out this z-score, which is approximately 2.33, that if I have a z-score of 2.33, that would give me a place for the top 1% of the data. It's to the right of the z-score 2.33. And certainly if you want to go out to 5 decimal places, you can, but usually not necessary to do so. All right, what else do we need to know about this? So then, we are now going to consider something called a data transformation. And sometimes people have seen this, but they didn't know what people were talking about when they did it. Okay. So what we're going to do is we're going to take these ideas of the standard normal distribution, and we're going to do a data transformation which will be able to take any data set and make it look like this one. So you could be measuring water quality. You could be measuring the height of 2-year-olds. You could be measuring shoe sizes. Doesn't matter. You can take your data set and you can do this data transformation, and it will look like this artificial data set. And the formula for that is this. This is Z, which we've already talked about. What does Z signify? Z is telling me the number of standard deviations from the mean.
Is that
No, it's a sigma. Okay? This X represents a data value. This Greek letter mu represents the mean. And the Greek letter small sigma represents the standard deviation. So what we're going to do then is we're going to say for any data set, doesn't matter, I can take that data set, find the mean, find the standard deviation, and then if I put it into this formula, it will take all my data values and change them into z-scores, which will have a mean of 0 and a standard deviation of 1. Now that doesn't mean they'll be bell-shaped necessarily, but they will be transformed to have a mean of 0 and standard deviation of 1. That's how this works. And it's really helpful for us to be able to do that. It gives us information about our data set. However, if our data set is bell-shaped, then we're going to say that our data set follows the normal distribution, and now we can predict what would happen. So, for example, let's say that I have I want what? I want to get rid of this here. Let's say that I have something like cost of TVs. And let's say that the cost of these televisions, when I look out there and I say, okay, what are the different televisions that I have in a particular category? How much do they cost? That it's bell-shaped. If it's bell-shaped, then I can use these tools. And I'm going to say that the mean is $500. And let's say the standard deviation is $20. Yeah. And then I'm going to say, what would be the probability of having a TV cost more than $530? If I know the mean and I know the standard deviation, then I can take my data value, my $530, and I can change it into a z-score. So now z is 530 minus 500 divided by 20. Now you got to be careful, order of operations and all that. 530 minus 500 is 30, and then divided by 20 would be 1.5. So now what I'm actually asking is, what's the probability of having a z-score greater than 1.5? And so, you know, I pull up my software, click the button here, 1.5. It's about 7%. So again, the concept here is that I use my mathematical formulas. Based on these ideas, I can predict what I think is going to happen. And I can predict it for any price, more than or less than, either direction. And I can predict for any particular interval through the processes that I showed you. We can make this happen for all those things. Questions?
What technology did you just use?
I just used the thing that I had up here previously, which is from the University of Iowa. But again, you could use StatCrunch or Excel. And I should probably post those, right? University of Iowa things, yeah, they're really handy. Okay, so I will do that. But certainly, if you Google normal distribution calculator, you'll get 100 of them. So they're out there. All right, so this is our power of prediction for these kinds of things. But now we also want to be able to go from probability to data values. So if I ask the question, what data value is the top, let's say, 20%? So I want the data value that cuts off the top 20%. Where would I find the highest 20% of these numbers? Well, previously I was using data to get z and get the probability. But now I want to put in the probability, get the z-score, and from there figure out my data. So once again, using my technology, I say, all right, I want that maximum probability, or I want the top probability of 20%. I put in 0.2, I get a z-score of 0.8416. So from a probability on the right of 20%, I get a z-score of 0.8416. That means here, 0.8416, that's my horizontal z-score based on this area of 0.2. Now that I've found that, I can use my data transformation where I say 0.8416, that's the z-score, equals, I don't know my data value now. I'm looking for x, minus 500 divided by 20. This is the only algebra we'll ever do in this course. I want to solve for x. How am I going to do that? Well, I'm going to multiply by 20 and then add 500. And so then that's about 17. So that's about 517. So that's telling me that if I have the data value for the top 20%, the mean here in the middle is 500. 517 over here would give me my top 20%. Now, this is not exact, okay, because my numbers are constantly changing. Is it really true that my televisions have a mean of 500 and a standard deviation of 20? Tomorrow, it'll be different. Somebody will come up with a new model, and they'll say, okay, well, let's put this thing on there. Or somebody will say, let's have a sale, and it'll be different. So these are not exact things, but this is ballparking it. This is giving us an idea of what to look for. So these formulas, these mathematical formulas look great. And you click things on the computer and it comes out. It's really nice. But don't trust these numbers, okay? These means and standard deviations, these are measurements and they constantly change. So you can't say, I know exactly what's going on, because you don't. But it'll give you an idea of possibilities, things to look for, concepts to understand. Now, as it turns out, this particular software is even better because if you have this software, you can change the mean and standard deviation right in the software. You don't even have to do the algebra anymore. So if you say the mean is 500 and the standard deviation is 20, I want it to be 20%, 517. So yeah, you don't even have to do algebra anymore. Just click. There it is. All right. So these are the main things that are going to be on your homework. Finding z-scores, so you understand those, and then doing the data transformations. So you have your data sets and you can make them into z-scores, and then to be able to figure out what those things are. But for completeness, let me just mention a couple of other things. And those are, how do I know if my data is bell-shaped or if it is not? Okay, how do I assess the normality of something? Now your textbook goes through and describes this, and I'm just going to show you an example here. Jeff, I'm going to use your data set here. And so I'm going to go out here to StatCrunch. And I think I can do this. Let's just put this sheet out here because I want to paste it transposed. Fine. Okay, so here's StatCrunch. So here's your data set. And if I graph it, let's just do a dot plot. Looks like this. Okay. And then I say, is that bell-shaped? How would you say no? Is most of the data in the middle? No. Doesn't look like it. Is it symmetric? No, not symmetric. But if we really wanted to say, is it normal? Is it bell-shaped? We have this thing called a QQ plot. And if I do a QQ plot with a correlation statistic, it looks like this. And I ask the question, do these dots fall on a straight line? Roughly, they do. Correlation is 0.955, and there's a chart in the textbook that tells us that's kind of significant. But you can tell that they don't exactly fall on here, and that these are definitely away from it on this end. And these are away from it on this end. So if you're going to say, is this straight? No, it looks like it's curved. It's kind of curved that direction. But then this thing up here might say, it's kind of bell-shaped, or it's bell-shaped enough that we can pretend it's bell-shaped. So I don't put a lot of, I don't know how to say this, but I don't believe this very much. Can I really tell if my data is bell-shaped just by doing this method? Even though there might be science to tell me one way or the other, I'm willing to say I'm not sure exactly. It would seem more reasonable that I would kind of look at a histogram, perhaps, and see if it actually comes out to look that way. But then there are other methods where we use things like chi-squared. Later on, we'll talk about that, to actually see if it is or if it isn't. Again, your textbook talks about this and describes more about how you can determine if something's bell-shaped or not. And the fact of the matter is, if you know your data values are not bell-shaped, then that limits how you can use this z-score stuff. You really should not be using z-scores for this kind of prediction if it's not bell-shaped. But then there are other things you can do. You can like take the logarithm of your data. Maybe that'll make it bell-shaped. So there's crazy stuff out there. We're not going to worry about that. We're just going to work with the stuff that we have. And in the problems, it will say, assume that you have a normal distribution, and then you do the rest of the problem. And many times, the numbers that you'll have will be close enough to be bell-shaped, so you're not going to worry about it. All right. So that's hopefully enough information for you to be able to